Okay, now let's see if we can get the Arrhenius equation. What we can do with this. So the Arrhenius equation gives a connection between the rate constant and the activation energy in a reaction. So rate constant equals A times e to the power of minus EA divided by RT. Now let's dissect this equation a little bit, what this actually means. So A, this is just simply an calibration factor, and in a way it has the function of showing how collisions actually work, how successful they are. EA, this is the activation energy that we need. In order for a reaction to work. R is the universal gas constant, and this is 8.3 joule per mole and Kelvin, and this here is the temperature in Kelvin. Okay, so what can we do with that? Now, of course, we have got this E in here, Euler's number, and what we can do is we can use this equation, we can transform this equation. So let me write this down again, equals A times e to the power of minus EA over RT. And in order to get rid of the E, we take both sides with the inverse function of E, and the inverse function of E is ln. So what have we got? What have we got on the left-hand side? We've got ln, the natural logarithm of k, equals, and then we have got natural logarithm of this expression, E minus EA over RT. And we know that the rules of logarithm, what we can do according to these rules, we can simplify this to ln A plus, because we've got a multiplication here, ln e to the power of minus EA over RT. And we know that ln and e cancel each other out. So what we've got is ln of the rate constant equals ln A minus, and what have we got here? We've got minus EA over RT. And let me write this in a slightly different form. Let me write this as ln k equals ln A minus EA over R times 1 over T. So what does that give me? Well, can you see it, what this is? Indeed, it is the equation for a straight line. If we say this here is y equals c minus mx. Or I can write it as y equals minus mx plus c. So how would this then look like? Well, let's draw a coordinate system. So what do we plot on the y-axis? On the y-axis, we plot ln k. What do we plot on the x-axis? Well, on the x-axis we plot 1 over t. And what we get is really a straight line like this. The gradient of this straight line would be negative EA over R. And if we extend this gradient, we would get this point here, ln A. So what we have done is we have taken this rather unsavory looking Arrhenius equation and we've converted that into a straight line. And what we can do now, of course, is we can find a relationship between our ln of k, the ln of the rate constant, and 1 over t. So if we make t very large, so t is very, very large, then 1 over t becomes very small and it becomes 0. And if the temperature is very, very hot, if we are very hot, then our ln k is, so ln k is the same as the ln A as this collision factor. If the temperature goes is becoming very small, then we are becoming very large with 1 over t. And our ln k goes into the negative range, and an ln k negative, so if ln k becomes negative, smaller than 0, then k becomes smaller than 1, because ln of something smaller than 1 is a negative number. So the rate constant becomes smaller if t also becomes smaller, because then we are going in this direction here. So with that, we can also easily find, if we determine our ln k and our t, or rather we have different t's, different temperatures, and we determine the ln k, we can actually calculate what our activation energy is, because this R really is just simply nothing but an ordinary constant, which is very well known. So hopefully this video helps you to demystify a little bit this famous Arrhenius equation that really makes the link between kinetics and thermodynamics in the activation energy. So that's thermodynamics. I hope this makes sense. Thank you very much for watching.